Stop talking, please. Yeah, what's up, Francis? How much are we learning?
Yeah, like how long are we learning today?
I don't like 45 to an hour.
Okay. Oh, sounds good.
Okay. Why? What's up?
Nothing. I'm just wondering how, like,
Oh.
mentally preparing myself.
Okay. I don't know if there was something the matter.
Oh no, I'm not.
Okay.
I'm just curious.
Before we get this show on the road, do you guys have questions on anything? We asked you guys to do like 1 through 12 as your problem set. Mira?
Should I show you what I look for?
At the end of class, I'd be happy to check it in. Because that might be similar to the kinds of things that you would be asked to do on like a potential homework quiz, which may or may not be coming up.
We still do that?
Yeah.
Uh,
Wink, wink, nudge, nudge. Yes, we still do them.
Is that next class is Saturday?
Hmm.
There's only 14 more days of this class. Actually, 16. Huh. Okay. Sorry. I love this class, Mr. Coolidge.
I know you do, Francis. I can tell.
Could you please just 8?
8. Yup. Let me grab that. All right, let's do 8. It says you do not need to graph the function. I'm going to graph it anyway because we're going to assign the graphing problems also from this pertaining to the same set of topics. So this will just serve as good as any example. So it says find the vertical asymptotes, horizontal asymptote, zeros, y-intercept. You do not need to graph the function. Okay, so first thing I'd want to do here is I'd want a factor, right? So the numerator, I'd be looking for the two things that multiply to give me negative 24 and add to give me positive 5. Those two things would be anybody? Should be like a 3-second problem. How about 8 and negative 3? Okay, so I guess let's find the vertical asymptotes first. How do I find the vertical asymptotes? I set the denominator equal to 0 since there's no reducing to do. And then maybe we'll find the x-intercept next. How do I find the x-intercepts? Set the numerator equal to 0. But remember, we're going to write these as points rather than just x equals so that we don't confuse them with our vertical asymptotes. Then we'll do y-intercept. How are we going to find the y-intercept? Yeah, plug 0 in for x. So that's going to be negative 24 over 5. Or over negative 5, so that's going to be positive 4.8. And again, I'm going to write that as a point, so I don't accidentally confuse it with like a horizontal asymptote or something else. So far, so good. Next, we'll look for any horizontal or slant asymptotes. To do that, we need to look at the degree of the numerator and the degree of the denominator. What's the degree of the numerator? 2, right? What's the degree of the denominator? 1. Because 2 is greater than 1, that tells me we have a slant asymptote. To find that slant asymptote, we need to do polynomial division. Because the denominator is monic, I can do that division as synthetic division. So this piece right here is the quotient. That tells me my slant asymptote is y equals x plus 10. Now, this particular question number 8 doesn't ask you to graph this. In fact, it says do not graph it. I'm going to graph it anyways because I'm going to assign 13 through 24, which are basically the same problem plus graph it at the end. So might as well just do this one since we've come this far and we took care of the hard part. So I have the vertical asymptote at x equals 5. 1, 2, 3, 4, 5. So we draw the vertical asymptote with a dashed line. We have x-intercepts at -8, 0, and 3, 0. There's 3, 0. 1, 2, 3, 4, 5, 6, 7, 8, 0. We have 4.0, 4.8, 2, 3, 4, 5. So just a hair under 5. And then we have this slant asymptote at y equals x plus 10. So if I wanted to plot this, how many points do I need for that? It's a straight line, so I just need 2, right? Since there's that plus 10 at the end, I'm going to pick negative values so I'm not like just off the charts on this guy. So let's say I pick -8 and then like -6. So when I plug those in for x, I'd get 2 and 4. Let's go ahead and graph that. So I have the point -8, 2, and then -6, 4. So there's that thing going on way into my work, but whatever, that's fine. All right, so with what I've sketched, I know that my function's end behaviors have to follow the asymptotes. So this piece, if it's going to go through those and still follow this one, it's got to look like that, right? Everybody feel good there? I then just need to check to see what this side is going to look like. So to check that, I'm just going to look at some end behaviors. So I'm going to look what happens as x approaches 5 from the right. So if I think about plugging in a number a little bit bigger than 5, that's going to be positive, that's going to be positive, and that's going to be positive. Right? Something a little bigger than 5 plus 8, positive. Something a little bigger than 5 minus 3, still positive. Something a little bit bigger than 5 minus 5, still positive. Everybody agree? So I know it's going to be like this spot up here. Oops. Is it going to be that spot up there? That seems like it's got to be. Oh, I see what it's. So it's going to be. That's a bad. Yeah, so this is just like. So if we do this all the way up, it's going to do one of these guys. That's where it's going to be. Emmy? Sure. Yes, Kirsten. Down here?
Yeah.
I just picked the x's and then plugged them in to find the corresponding y. The x's I picked were arbitrary.
Oh, okay.
Yeah, I just picked them because that plus 10 there, I wanted to have points that were like going to be on what I drew, even though I guess I ended up going through all my work anyways because my graph got big. This is probably why I said not to graph these ones. It's because it was going to get it hard to fit on a sheet of paper because the numbers just got kind of big. But what do you guys think? So on your homework quiz, you just be asking you to find like the parts. Wouldn't ask you to graph anything. So you should be able to do no domains and discontinuities and find these key features just like we did here, which should be okay, that none of those are too difficult to do. The hardest part is usually just remembering what to do for which. What do you guys think? Should we do another? Okay. I'm going to just grab the, like the 13 through 24 and drop that in when I'll let somebody pick their favorite number. We'll just do that one. So this is will be part of tonight's homework set. It's just doing the same thing that we did last time. You're just putting it all together into a graph just like we did here. So who wants to pick their favorite number between 13 and 24?
22.
22, says Brody. Okay. Any objections there? I hope not. It's a pretty innocuous number. All right. So again, the directions say sketch a graph, make sure to include all the same stuff. So I'm just going to start by finding the stuff. But the first thing I'm going to do is factor. I notice the numerator is a difference of 2 squares. So I just factor that right quick. Any questions there? Okay, now let's start finding those key features. What's the vertical asymptote going to be here? -2. Everybody see how she got that? Setting the denominator equal to 0 and solving. How about the x-intercepts? 1 and -1. Remember, we're going to write those as points, though. Everybody okay with how she got that? Setting the numerator equal to 0 and solving. Who can tell me the y-intercept? Not 0 over 2. 0, comma. Nope. Negative 1/2. 0 minus 1 is negative 1. 0 plus 1 is 1. Negative 1 times 1 is negative 1. And the denominator is 2, right? So it's negative 1/2. If you would have written it down, you would have gotten it wrong. It's only because you're trying to do it in your head that it's like, oops-a-daisy. I added when I should have multiplied. I think is probably what you did there, Kirsten. Yeah. Happens to the best of us. I almost said yes, but then I was like, ooh, I looked a little closer. That's not quite right. Next up, we've got to find those horizontal or slant asymptotes. Which one do I have in this case? What do I need to look at to tell? The degrees. What's the degree on top? What's the degree on bottom? 1. Since 2 is greater than 1, that tells me we have a slant asymptote. Very good. How do I find that slant asymptote? We do polynomial division. Now, if I look at the denominator, I can do synthetic division. That's what I would prefer to do here because it's usually a little bit easier. Now, there's one thing I need to be careful when I set up this synthetic division, though. You got to remember that 0 between the x squared and the negative 1, right? Because we have no x term there. So I'll just kind of bang through that guy. So I'm under remainder constant x. So that guy's our quotient. So I have a slant asymptote at y equals x minus 2. What do you guys think? So far, so good? All right, let's start sketching ourselves a picture here. And draw a straight line, that would help. Okay, vertical asymptote at negative 2, so I like to put those guys in first. Okay, and I have x let's do this other slant asymptote. So I'll just make a quick little xy table. So I have 0, negative 2, and then 2, 0. And then let's plot some points then. I have 1, and then negative 1 for zeros, and then 0, negative a half. So it's pretty clear to me that this section of my graph has got to look like that. Now the next question is the other section going to be over here, or is it going to be down here? To check, I'm just going to look at the end behavior. So I'm going to look at what's happening as x approaches negative 2 from the left. So when I plug in something a little less than negative 2, that number is going to be negative. That number is going to be negative. And that number is going to be negative. Everybody's okay? That's going to give me a negative number, right? Negative times negative divided by negative is going to be a negative. So that means that this arrow should be pointing down. So I want the section down at the bottom of the graph there. What do you guys think? What's the best way to check this? Graph it on your calculator, look at the picture, absolutely. You know, no big deal. What do you guys think? Does that feel a little bit better doing it a second time? So again, for the homework quiz next time, you'll have to do stuff like you did in that 1 through 12. So like finding domains and, you know, finding those key features, writing end behaviors, stuff like that. Feel okay? I know there's a light that's kind of, bulb needs to be replaced. I emailed maintenance about it. They'll get it at some point. It's okay. All right. You guys feel okay here? It's all right? Okay. So on to 14.2. Talk about solving rational equations. And we're just going to look at examples here and just talk about one technique to use. There's lots of different ways you could do this. I'm only going to teach you one technique because it works in every single situation and it's never going to be like really inefficient. It'll always be pretty okay. And rather than doing a bunch of different techniques where you have to try to decide which one is the best one to use where and get confused between what do I do for one versus another, we're just going to do one technique for every problem. If all you have is a hammer, every problem looks like a nail, so that's what we're going to go with. Everybody cool? You're excited. It's a big smile. All right. So the technique we're going to be using is called clearing fractions. And the idea is we want to multiply both sides of our equation by the least common multiple of all the denominators. So if I look at this example, remember I can always write a number as something over 1. The only denominators I have are x and 1, right? What is the least common multiple between 1 and x? It is not 1. So 1 would be like greatest common factor. So to find a least common multiple, you need each distinct prime factor to the largest, well, let me do a little better than this. It'll be a little bit more specific. Least common multiple of A and B is the distinct prime factors of A and B to the greatest power of each distinct prime factor in A and B. So for example, the least common multiple of 2 and 3. The prime factorization of 2 is just 2 to the first, right? The prime factorization of 3 is just 3 to the first. So the least common multiple of 2 and 3 is going to have a 2 and a 3 in it. And the biggest power on the 2's is 1. The biggest power on the 3 is 1. So the least common multiple of 2 and 3 is just 2 times 3, or 6. What's the least common multiple of 2 and 4? So the prime factorization of 2 is just 2 to the first. The prime factorization of 4 is 2 squared. The only distinct prime between them is 2 and 2. Or between them is 2, correct? And the greatest power on 2 is the second. So the the least common multiple should be 4. Right? Notice that the least common multiple is divisible by each of the A and B. Let's do another. Least common multiple of, 12 and 18. The prime factorization of 12 is 2 squared times 3. The prime factorization of 18 is 2 times 3 squared. So my least common multiple is going to have a factor of 2 and 3 in it. What power of 2 should I have? Should be to the second. What power of 3 should it have? Should be to the second. So that should be 4 times 9, 36. Go ahead. What do you guys think? You get the idea? Or no? Do you want another example? Okay. You just ask, man. It's fine. We got lots of time. Let's do like 27 and 24. So again, we start with the prime factorization. The prime factorization of 27 is 3 cubed. The prime factorization of 24 is 2 to the third times 3 to the first. What are the two distinct prime factors there? 2 and 3, right? Good. What power should the 2 have? 3, because the biggest power of 2's is to the third. What should be the power on 3? To the third, because the biggest power on the 3's is to the third. So this is going to be 216, I think. Yes.
What is the prime factor?
So the fundamental theorem of arithmetic says every number can be written as a product of powers of primes, and that can happen uniquely. So like 27 is 3 times 9, and the 9 is 3 times 3. So 27 is just 3 times 3 times 3, or 3 to the third. So that's all we're doing. I'm just doing it quickly in my head, because I'm a math teacher and I can do that kind of thing.
And primes are just numbers that are divisible by themselves.
Can only be divided by themselves in 1, right? Or they're only positive divisors. Cool. So what does that mean for a situation like this, where we have 1 and 4, right? Or 1 and x. So let's grab this guy again. I'm just going to bring him back down here. So we need to start by finding the least common multiple of 1 and x, right? Well, 1 is just equal to 1, right? There's no prime factorization to do there. Everybody's good with that? Can we factor x at all? No, right? That's a prime polynomial because it's not factorable. So my least common multiple is just going to be 1 to the first times x to the first, or just x. Everybody's cool with that? So that's what I'm going to multiply both sides of my equation by, is x. So far, so good. So I'll start by kind of just distributing that x through. What's x times x? Okay. What's x times 3 over x? 3 is correct, right? Again, you're thinking about it as like multiplying fractions, and then the x's can reduce. If you can do that in your head, I encourage you to do so. It's where you want to be at, is being able to see that in your head. If you don't see it right away, I'll write out the fraction and reduce it a couple of times before we just move on and accept it like this is, we don't have to do that every time. So we're left with x squared plus 3 equals 4x. What type of an equation is that? Polynomial, but more specifically, since it's a degree 2 polynomial, we'd say it's quadratic. How do we want to solve a quadratic equation? Well, we want to first make it equal to 0. So let's subtract that 4x from both sides. And then to solve this quadratic equation, we could either, what methods might we use? Factor or quadratic formula, right? Either one of those would be fine. In this circumstance, which one do you think I'm going to pick? Factoring, since the leading coefficient is 1. If it's factorable, it should be pretty easy to do. So I'm going to start there. Are there two numbers that multiply to give me 3 and add to give me -4? -1 and -3 is correct. So then I can set each factor equal to 0. And I get the solutions 1 and +1 and +3. Excuse me. But we're not done. What do you mean we're not done, Mr. Kulik? You have 2 answers here. Like, why aren't we done? Well, remember, what we just solved technically was a quadratic equation, right? We solved this polynomial. The domain for a polynomial is all real numbers. Always, every single polynomial. But the original problem was a rational whose domain is not necessarily all real numbers. So it's possible that one of these solutions, or both of these solutions, fell into the hole in the domain of that rational function. So we need to make sure that we're checking our answers to see if that happened, because our answers may not all work. So the way to check that is actually quite easy. All we need to do is take our answer and plug it into the denominator and see if we get a 0 denominator. If I plug 1 into x, does that make a 0 denominator? No, Mr. Kulik. What if I plug the 3 in? Does it make a 0 denominator? No, Mr. Kulik. The only number that I could plug into that x to make a 0 denominator would be 0. Clearly 1 and 3 are not that. So that's all the checking you need to do. They're both done. They both worked. It would make that particular solution extraneous. Because what's happening is the equivalent polynomial, the solution to that falls in the hole, or the asymptote, in your domain of the rational. We'll see that happen here in a moment. And that could happen with 1 solution, 2 solutions, all your solutions. Let's do another example, though, eh? Drop in another example problem. You guys feel okay about the finding the LCMs though so far? Okay. So again, I look at this problem, I see only one denominator. So really I'm looking for the least common multiple of 1 and x plus 1. Well, there's no factoring to do for 1. How about x plus 1? Can that factor at all? Nope. So what's my least common multiple going to be? 1 times x plus 1, or just x plus 1. Does everybody feel okay with how we found that LCM? If you can't do that, this method's not very useful to you because you got to be able to find those LCMs. So I'm going to multiply both sides of our equation by x plus 1. And just as an aside here, technically speaking, any common multiple will work, but you really want to use the least common multiple, because by picking a not least common multiple, you're just making a bigger degree polynomial. And how much harder is it to solve a cubic polynomial versus a quadratic? It's a lot harder, right? You have to do like the synthetic division stuff probably, and it's kind of a nightmare. You want to make sure that polynomial is the least degree that you can make it. So you really want to make sure you're finding that least common multiple, because it's going to make your life way easier. Okay. So multiplying both sides by x plus 1. So again, I got to multiply it to every piece. So x times x plus 1, I'm just going to write it like this for now. When I multiply x plus 1 times 6 over x plus 1, I'm going to think about that as multiplying two fractions. So multiply the tops together and the bottoms together. And then 0 times anything is 0. I notice that fraction in the middle can just reduce now to 6. Ooh! I like it when all the fractions go away, right? So if I just distribute that x through now, I have x squared plus x minus 6 equal to 0. What do we find? A quadratic. How are we going to solve this quadratic? Looks like a good candidate for factoring. Are there two numbers that multiply to give me -6 and then add to give me +1? 3 and -2 will work. So my solutions are -3 and +2. Are we done? No. What do we still have to do? Yeah, we have to check for extraneous solutions. So if I go back to the original, if I plug in -3 in for into the x plus 1, does that make a 0? No. If I take +2 and plug it into the x plus 1, does that make a 0? No. What does that tell me? They both work. They are not extraneous. So extraneous are ones that do not work. These are just solutions. Okay, let's do another. Got a couple more examples and then we'll be done for the day. How's that sound? Pretty good, I'd hope. Yeah, Mira, what's up? Sure hope so. All right. Here's our next one. Oh no, Mr. Kulik, look at this complicated looking thing. Yuckarooskies. Guess what I'm going to start by doing? I'm going to start by factoring, because it makes finding the LCM so much simpler if everything's in their factored form. So if I look at 2x over x minus 1, any factoring to do there? Nah. What if I look at 1 over x minus 3, any factoring to do there? Nah. How about 2 over x squared minus 4x plus 3, any factoring to do there? Yup. Is it in the numerator or denominator? Denominator. How does that denominator factor? Excellent. X minus 3, x minus 1. So we're going to start by looking for the least common multiple of these three. X minus 1, well, that's not factorable. That's prime already. X minus 3, that's not factorable. That's prime already. And then x squared minus 4x plus 3, we've already written in its factored form. So my least common multiple needs to have an x minus 1 in it. It needs to have an x minus 3 in it. Those are my two distinct primes. The biggest power of my x minus 1 is to the first. The biggest power of my x minus 3 is to the first. So my least common multiple is just x minus 1 times x minus 3. So we feel okay in how I got to there? So we'll multiply both sides by that guy. All right, this time I'm not going to write out the reducing when we do this distribute. We're just going to try to see it, because that's where I eventually want you to land. So if I multiply x minus 1 times x minus 3 to the first fraction, what is going to reduce? The x minus 1s, right? Everybody see that? What's going to be left over after the x minus 1s reduce? Well, we have the 2x and we have the x minus 3. Can everybody see that? When the x minus 1 times x minus 3 multiplies to 1 over x minus 3, what will reduce? X minus 3's. What are we left with? Well, we have the 1 and then the x minus 1. And then when x minus 1 times x minus 3 is multiplied by 2 over x minus 3 times x minus 1, what reduces? The x minus 3 and x minus 1. The only thing that's left then is the 2. Does that look okay to everybody? I'm now just going to clean this up and see what kind of an equation I'm left with. Obviously, it's polynomial, but it is quadratic, I see, because it's degree 2. I'm going to move everything onto one side and combine some like terms. That leaves me with this. Now, to solve this equation, what do you think I should do? I would use the quadratic formula here. Why? Excellent. The leading coefficient isn't 1 anymore, so even if it is factorable, which it might be, it is, I know already. But it takes that, it's that longer factoring method, and like, to me, I might as well just use the quadratic formula because it's guaranteed to work and it's Not really any slower than doing the long factoring. Quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2 times a. So negative of a negative is positive. Negative 5 squared is 25. Minus 4 times 2 times negative 3 is 25 minus 24, or minus a negative 24. So that's 49. The square root of 49 is 7. 5 plus 7 is 12 over 4, which is just 3. And then 5 minus 7 is negative 2 over 4, or negative 1/2. Everybody's good to go so far? All right. Still need to check, though. Where do I check at? The original equation. So we're going to plug these into the denominators on the original equation. If I plug 3 into x minus 1, do I get a 0 denominator? No. If I plug it into x minus 3, do I get a 0 denominator? Yes. At this point, I stop. That solution has failed. It is extraneous. And I'm just going to move on to my next answer. I don't need to keep on checking. As soon as I get 1 0 denominator, that is enough to stop. Everybody's good? Okay. Go back up. If I plug negative 1 into x minus 1, does that make 0? If I negative 1/2 into x minus 1, does that make 0? I think I misspoke earlier. If I plug negative 1/2 into x minus 3, does that make 0? If I plug negative 1/2 into x minus 3, does that make 0? If I plug negative 1/2 into x minus 1, does that make 0? Do I get a 0 denominator from that one? Nope. So that answer is okay. I have left with one solution, x equals negative 1/2. The other solution is extraneous. Feel okay? How's this going? So far, so good? Pretty easy. If your quadratics skills are good, this is usually pretty easy. If your quadratic skills are this can be tough. All right, I got one more example, and we can be done. It's music to Francis's ears. I know it is. You are listening. I'm not saying you're not. I'm just telling you that, like, you asked me how long this was going to be, and look at the clock here. We're right here between 45 and an hour, right? Not a liar. All right. What am I going to do to start? I'm going to just do a quick factor, right? The only piece that can factor is that last part. And then just like the previous one, I get the same least common multiple, right? Do I have to write out everything to do that? I think at this point it's the same problem as last time, right? For the least common multiple. Is that feeling easier, that least common multiple thing, after we've done a bunch of these? Any kind of verbal answer would be okay when I ask a question like that. Okay. You don't have to like give me the unison patronizing like first grade answer, but just like a yeah, dude, I'm good. You know, whatever. Just yes, dude, I'll take it. Everybody's good to where we are here, yes? All right, let's start distributing. What am I going to get left when I distribute the x minus 3 times x minus 1 to the first fraction? Times x minus 1. What do I get when I multiply to the second fraction? Good. Boys in the back, keep it together. You got like 5 more minutes, and you can get goofy. And when I distribute to the last fraction, x squared. Everybody okay? All right, let's go ahead and distribute things through. Now I notice I have these decimals here, which I don't love, but if I look a little bit carefully, I don't think it's going to be much of a problem when I do the combining of like terms. So I'm not going to worry about it right yet. Because look what happens when I combine these guys. What am I going to get? Yeah, and when I combine those guys, what am I going to get? -4. And then I'm just going to move everything onto one side. And I chose to move it on the right-hand side because I want that x squared to be positive because it makes the factoring easier. And in fact, that x squared minus 3x minus 4, that's a factoring problem we've done already. So I get solutions of 1 and -1. But what's going to happen here? I check here, no problem. I check there. Wah, wah. All right. If I check this one, if I check here, wah, wah. Both of them failed. What does that tell me? No solution, because they've all run out. Oh. But no big deal, right? What do you guys think on today? It's okay? Yeah. All right. So your homework, there's 13 through 24. That was really just kind of continuing on with the 14.1 stuff. We just ran out of time to do a good, careful, slow graphing example. So I wanted to leave that part of the homework till we did some examples so you could kind of see what we're looking to do. And then based on what we did today, we're going to have, what's that going to be? 25 to 32. That's based on what we did today. What do you guys think there? It's okay? What's up? Okay. You said something, but it was fast and kind of quiet. And somebody like set a pencil down at the same time and it just like washed it out on me.
No, you're fine. I was just seeing like which 25 through what. I saw the word.
Oh, okay. All right. And I'm done.